Hello, everyone. Welcome back to the good stuff. And this is the AAS Journal Author Series. And I'm super happy to have Joe Weingartner here with us today. Hi, Joe.
Hi, Frank. How are you?
Good. Where are you at?
I'm in Fairfax, Virginia. We're about 15 miles west of DC.
When I was a wee little boy, about 10, I had a paper route around Fairfax and Alexandria.
Oh, is that right? What do you know?
Yes, I did. So there's a little tidbit for everyone out there. I had a paper route in that area. That's great. So you guys, are you opening up yet or opening up, planning on opening up?
We're waiting to hear, actually. We're supposed to hear in the next couple of weeks.
Okay.
So kind of in limbo right now.
Okay. ASU is tentatively opening summer B, that's TBD, and then fall, I think, is nobody quite knows yet. But
Okay, yeah. Our summer is definitely online. It's just fall we're still waiting to hear about.
Yeah. Okay. So people may be wondering, why in the world am I choosing a paper from 2001 to go over on this author highlight? And the reason that I'm doing that is some of you know that I do have a penchant for the evolution of the most cited articles in astronomy and astrophysics. And in 2001, this is the paper we're going to be talking about today, dust grain size distributions in the Milky Way and the Magellanic Clouds. And highlighted in big red there is the evolution of this article. So it started its rise, came into the top 50 at about 2004. Which I note is outside of the journal impact factor window. And then it had a steady rise up over the ensuing 7-8 years. And currently, as of March 2020 anyway, it sits in the number 7 slot. So it's one of the top 10 most cited articles published in the year 2001. And so this is my interest in this paper. So it's a classic, in other words, it's a highly cited classic. So at that point, this is going to be our segue into the article itself, which is dust grain size distributions and extinction in the Milky Way, large Magellanic Cloud, and small Magellanic Cloud. And Joe, take it away.
Okay, thanks a lot, Frank. So my co-author on this was Bruce Drain, and I had the really extreme good fortune of doing my PhD with Bruce. And so this paper actually grew out of one of the topics of my dissertation, my PhD. And so it really draws on two previous genuine classic papers, which developed the famous MRN model of dust. And so in this model, we have two populations of dust that are separate from one each another, one of which is graphite and one of which is silicate. And so we know that silicates are prevalent in the ISM. We see spectral features at 10 to 20 microns that are very clear indications of silicates. And then graphite was introduced to account for the UV feature at 2175 angstroms, which is a big hump in the extinction curve. Basically, there are delocalized electrons in the carbon hexagons in graphite, and the electronic excitation can produce that particular feature. So that was the reason why graphite was introduced. Okay. And so MRN, Mathis, Rumpel, and Nordseek, back in 1977, they found what was the best size distributions of these two populations to reproduce the extinction curve as was known at that time. So the attenuation of starlight is a function of wavelength. And then the second big classic was Drain and Lee in 1984, which built on that and introduced synthetic dielectric functions. So basically, rather than using actual dielectric functions for real silicate minerals, which we don't know which particular minerals are actually in space, constructed synthetic dielectric functions that were physically consistent and which could reproduce the observed infrared features. So those are the two real classics. And then this paper was kind of an updating of that model, of that silicate and graphite model. And so basically, it took into account more recent observations of emission from dust, which indicated that there were grains that were smaller than what were contained in the MRN model. So I should have mentioned the MRN model was a power law size distribution with a power law index of -3.5.
Okay.
And minimum size of 50 angstroms, maximum of 0.25 micron. And these are spherical grains in these approximations. That's grain radius we're talking about.
Mm-hmm.
And so then with the emission observations, you find that there is emission at wavelengths that are shorter than you would expect, given the expected temperature of the dust grains. And the way we understand that is there are some very small grains, smaller than that 50 angstrom lower cutoff in MRN, which, when they absorb a single starlight photon, get heated up so high that they can emit now at shorter wavelengths.
Okay.
And that was the evidence for this population of small dust grains. So the point of this paper then was to do an update to account for those small dust grains, okay? And so I was really motivated by another project I was working on, which was to model photoelectric emission from dust. So the dust grains absorb starlight, and then some fraction of the time, a photoelectron gets ejected from the grain. That's energetic compared to the gas particles, and so that can heat the gas up.
Okay.
And that ends up being a really important heating mechanism for interstellar gas. So my interest then was to model that quantitatively. And because the smallest grains are the ones that are most efficient at photoemission,
Mm-hmm.
we needed to come up with a size distribution that would include these small grains, but would still be consistent with the extinction curve. Okay, that was the basic goal of this paper. And so actually, a humorous point, originally this was just an appendix to the photoemission paper. And then we decided, Bruce suggested that we actually cut it off as its own separate paper and then added some more stuff like the Magellanic Clouds, for example. So I'm really glad he decided to force me to do that. That was a really good move.
Yeah, and it looks like from the title you had transitioned to cited also at that point.
Yeah. So basically we had submitted the paper just before I finished my PhD.
Okay.
And then got the referee report back. I think it was my first day as a postdoc. And and let's just say there was a lot of comments on the photoemission content of the paper. And so Bruce said, let's just go ahead and separate this part as a new paper and get that done, and then deal with the photoemission stuff. But we ended up adding on quite a bit to this as well in the process. Okay, so that was the motivation. The other good thing about sort of holding off on it for a bit is that Bruce had a postdoc at that time, Eigen Lee, and they were working on a quantitative model of the emission. And so we were able to sort of use their results in this paper, which was great, which was really helpful. So when I say small dust grains, the very smallest of those are actually polycyclic aromatic hydrocarbon molecules, so pH molecules, big molecules.
Awesome.
And we kind of just treat them as the smallest end of the grain size distribution because we don't really know which specific pH molecules there are in space.
Mm-hmm.
And so what Bruce and Eigen basically did was to assume that they had the right optical properties, that they could reproduce that 2175 angstrom hump in the extinction curve. Okay.
Yep.
And then they said, what kind of size distribution did they need of the pH molecules to reproduce the observations of emission from the diffuse ISM?
Okay.
And so what they found was the best size distribution consisted of 2 log normal distributions. And I think if we scroll to the next page, we'll see those in the text.
There's the model, there's the functional form of the size distribution.
Yeah, so go on to, can you go to page 2?
Page 2.
Yeah. Are you there yet or not?
Oh, you're not seeing it.
I'm seeing page 1 on my screen.
You might need to change your view to see the whole.
Oh, here it goes. Okay, now I see it.
Okay. So
okay.
Do you want to go to the second page?
Yeah, that's perfect. Thanks.
Okay, so we'll go to the second page. So this is the model.
Yeah, so 2 and 3, equations 2 and 3 are, whoops, I think, yeah, can you go back 1 page? Sorry.
Okay, we may be having a lag. I'm on the I'm on the second page. And so we see equations 2 and 3, 4 and 5.
And now I'm back to page 1 somehow. I guess this is,
Okay, we may be having a lag issue. You
I don't
may.
have any control over this, do I? Because I'm trying to scroll on my screen.
No, I'm controlling the flow of the paper, so you should be seeing the share screen.
Okay, now I'm seeing equations 2 and 3. That's good. So 2 and 3, equations 2 and 3 are the log normal size distribution that Bruce and Eigen got for the PAHs. And then over in equations 4, 5, and 6, that's going to be the functional form that we adopt overall for the graphite and silicate populations. And so in addition to that log normal population of the carbonaceous grains, we've got sort of a modified power law with a cutoff at large grain sizes. So power law, some curvature that we can allow onto that, and then a cutoff with some degree of sharpness at the high end size. So that's basically our assumed functional form for the size distribution. And then we considered various model extinction curves from Fitzpatrick et al. And so basically going back a little bit further, so Cardelli et al. In 1989 had discovered that extinction curves sort of fall into roughly a 1 parameter family. And they used the parameter RV, which is the ratio of visual extinction to reddening, as the parameter. And so basically, for most lines of sight, if you can just indicate what RV is, you can draw sort of the whole extinction curve over the whole wavelength range, usually with pretty good accuracy. There are some glaring exceptions to that, but for the most part, you have a 1 parameter family. So we considered a few different values of that RV parameter. 3.1 is typical for the diffuse ISM, and then larger values correspond to more dense environments. And basically in those denser environments, some of the smaller grains coagulate out onto the bigger grains. So yeah, so we took the extinction curves for those sort of average values of RV from Fitzpatrick et al. And then just basically went and fit the extinction curves to figure out what are the values of all the parameters in our model size distribution that would give the best fit. Okay, so that was basically the game. And then let's see some of the early figures, if you don't mind.
Sure, here we are on figure 1 and 2. Do you see that?
Don't see it yet. There's a little bit of a lag, it looks
we have
like.
a little bit of a lag here.
I'll just be patient for a moment.
Okay.
While we're waiting for that, I'll just also mention that in addition to fitting the extinction, we also considered the total grain volume in the distribution. So basically, we have some limits on the grain volume just from the abundances of the elements that make up the grains. And so we also had a constraint on that in our fitting to try and not use too much grain volume. Okay.
You see figure 1 up?
Yeah, I see figure 1. So I guess maybe we'll look at figure 2. So figure 2 shows size distributions for RV equals 3.1, so the typical diffuse ISM. And the upper panel there is the silicate. The bottom panel is the carbonaceous. And then the heavy line is sort of the MRN model for comparison. And you can see very clearly those 2 log normal distributions at the small size end for the carbonaceous dust. And then you see the sort of modified power law for each of those, and then the cutoff at the high grain size.
Yes.
Now, we also have that label 10 to the 5 BC in there. So BC is going to be the abundance of carbon in the 2 log normal populations. Okay, that's what that quantity is.
Is that an absolute abundance or relative to hydrogen or?
Relative to hydrogen.
Relative to hydrogen, okay.
Yeah, carbon relative to hydrogen.
And just for reference, solar is?
Oh, you had to ask.
I'm just curious.
I don't recall. I don't recall off the top of my head.
I didn't need to put you on the spot. Just curious.
I mean, it is one of the more abundant elements for sure.
Yes.
But yeah, I could tell you off the top of my head. So, so basically, we didn't really know in 2001 what that number was. So we constructed fits for various values. So from 0 up through 6 times 10 to the -5 for that abundance ratio.
So just to orientate myself, then a BC of 0 would be pristine gas. No carbon.
Yeah, no carbon in the log normal population. So you still would have carbon in the larger population, but not in the log normal population.
Okay, I got it. I'm with you.
Yes, that's strictly for the small grains that are responsible for the emission.
I'm with you.
So yeah, so basically we found good fits from 0 up through 6 for that parameter. And then as it happens, Bruce and Eigen found from modeling the emission that 6 was about the number they needed. So it's kind of neat. That's sort of the highest value we could fit well was what they concluded. So our interpretation is that likely that 2175 angstrom hump in the extinction curve is being provided by the PAHs. That's the main contribution to that feature. Now, why don't we go and look at some more of the figures? So that was, like I said, for RV equals 3.1, so typical diffuse ISM.
Right.
And there should be some figures for some other environments as well. If we go a little further down, probably
So
the same
figure 3 is for RV equal 4. And if you want to talk about that one.
Yeah, so you can see it's a little bit different. Also notice the largest BC you can accommodate in that case is 4. So we do, as expected, seem to see coagulation of the pHs onto the grains as you get into the denser environments.
A lot.
And the next figure presumably is 5.5, if I remember correctly.
That would be, whoops, hold on here. That would be figure 4. Yes, it is.
Okay, yeah, so there we can, again, see the modification to the
Yep.
size distribution.
So BC is now 3 at max.
Yes. And so you also see it says case A on these figures. So this was basically doing the same fitting procedure that we did for the RV equals 3.1 case, where we included the constraint on the total grain volume.
Okay.
But it turns out you can get by with less total grain volume in the denser environments than you can in the diffuse ISM. So we also defined a case B that we prefer, where we just set the volume in those denser environments equal to the total grain volume that was in the RV equals 3.1 case. Just because it seems unlikely that as you go into the denser environments that you lose grain mass somehow. So that was the case B that you're going to see exactly in the next figures here. So figure 6 here for
correct. So figure 6 I'm on, and we got case B up. Yep. And definitely some, let me decrease the size so just people compare them side by side. So case A on the left, case B on the right. And yes.
Great, okay. Thanks.
Sure.
And so then presumably the next figures I think would actually show the fits. So yeah, if you look at the figure at the lower right on this page, I guess figure 8 probably, or figure 7. It looks
figure 7,
Yeah, so there you have a log-log plot, and you can see the fit to the extinction curve, you know, from the infrared into the UV over the full range for which data was available. That big hump you see there on the right, that's that 2175 angstrom hump I was talking about, that we believe the pHs are responsible for. And then the following figures basically show the same thing, just show the fits for each of those environments, but also show you the contribution of each component in the size distribution. So you can see how it breaks down.
Very nice. Okay. There's 2 different BCs on those. Got it.
Yeah, so basically show the case where BC is 0, so we don't include those pH molecules, and we just have the graphite responsible for the hump. And the case where basically the pHs are doing all the work. Like you can see a little bit of a hump there in the pH component, but or sorry, in the larger grain component, but basically the pH is doing all the work in that case.
Yep.
Now also we included one particular sight line to a star, which you know, had a really unusual extinction curve for its value of RV. So just checking, can the functional form that we adopted work for that bizarre case as well? And it worked just fine. So that was the section 3.1.3 here on the screen.
Right, HD 210121.
Yes, And then I think the next part of the paper probably was just showing results of the grain model that might be of use to people, observers in particular. So we should have a couple of plots in there. If we go a little bit further.
So I got to ask, what is it that's so peculiar about that HD star?
I don't know. I mean, good question. It just apparently it has just an unusual mix of grains compared to what most sightlines do.
Okay. Do we know if
So
it's like a mixed sequence or an HEV star or something like that? So maybe it's...
No, oh, I don't think so. No, I mean, it isn't the star itself. It's the region of ISM that the light traverses on its way here. Yeah,
Okay.
so nothing really to do with the star itself. Just whatever reason, there was a cloud in the ISM that just had unusual dust properties.
Yep. Okay.
Yeah, so figure 14 then, we sort of extended the wavelength coverage of the extinction from the model beyond the Lyman limit. So usually you can't really look at extinction beyond the Lyman limit because you have too much neutral hydrogen that just absorbs all that radiation.
Mm-hmm.
But you know, if you have an ionized region, you have access to wavelengths beyond the Lyman limit. If you're doing high redshift astronomy in particular, it can be useful to have that data. So we provided that there. Yep. And similarly in 15, figure 15, we're just showing the albedo and the scattering asymmetry parameter. It tells you how asymmetric the scattering is from the grains. Again, just in case that's useful for observers, for modelers. So that was part of what Bruce encouraged me to do to try and make this paper more useful to a wider range of people so that it would get more citations, I guess, in the end.
Can you elaborate a little bit on what you mean by the asymmetry parameter G equals average cosine theta? What is?
Yeah. So basically, if you had isotropic scattering of the radiation off the grain,
okay,
then that would be 0. So basically, you'd have as much scattering at theta equals 0, the forward direction, as theta equals pi, the backwards direction.
Okay.
And then any deviations from 0 are telling you that the scattering is asymmetric. So you have more scattering in one particular direction compared to another direction. So yeah, that's what that's telling us. And the albedo is just the scattering cross-section divided by the total extinction cross-section.
Yes.
Okay, and so then we looked at the Magellanic Clouds. So the Magellanic Clouds are interesting galaxies. They have low metallicity compared to the Milky Way. And so we just wanted to see, would the same model do a good job in the Magellanic Clouds? And basically the same thing, did the fits, used the same functional form for the size distribution. Got different size distributions, but still the same overall functional form, did a good job of fitting the extinction curves. The SMC is particularly interesting. Look at the SMC, you really don't see that 2175 angstrom hump in the SMC.
Here we go, figure, for example, 22. So your comment there, would this mean that the grain size distribution changes as a function of the metallicity of the galaxy?
Yeah, it seemed like it. Although with the SMC, I suspect that there probably are some pHs in there that we're just not seeing, that the line of sight that we're looking along was affected by radiation from hot young stars in that environment that might have destroyed the PAHs. There is more recent evidence that there could be some sight lines in the SMC that would indeed show pH presence. So, so yeah, you're probably seeing a different size distribution, a different metallicity galaxy, but maybe not as extreme as it seems from this figure. Okay, and then let's see, I think that kind of brings us close to the conclusions of the paper at this point.
So we're looking at figure 24 here, which is the last one in the paper. And then we head into the conclusions.
Yes, I'm not seeing 24 yet. Give me a moment for it to show up
Yeah,
on my
weird.
screen.
Why we have such a
I think,
lag here.
yeah, such a lag. Yeah, I think 24 should be a figure showing observed grain size distribution of grains that are streaming through the solar system. So basically, as the sun moves relative to local ISM, from our perspective, we have a wind of ISM coming into the solar system and bringing dust grains with them.
Right.
And then those actually can be detected by satellites. So the Ulysses satellite in particular, but
Mhm.
also Galileo and Cassini. And so you can get roughly a mass distribution of the grains that are hitting those detectors in the solar system. And so the triangles here are meant to be the data from those observations.
Right, for
And
sure.
then the curves are some of the different size distributions that we constructed in this paper. And obviously, there's no agreement there at all, right? It's terrible. And so we kind of understand what's happening at the small grain sizes, which is that those grains don't really make it into the solar system because they are excluded at the heliosphere. You have a shock where the solar wind hits the ISM and it
Okay.
compresses the magnetic field, and the grains are charged. They end up cycling around the magnetic field. They don't get into the solar system for us to observe. So we're not too worried about that. What is really bizarre is that you see all those large grains, and those large grains would contain mass that we just don't think is available based on the abundance constraints.
Yeah.
It's really hard to see how you could have those grains with all that mass and simultaneously have enough small grains to produce the extinction that we observe, because those large grains couldn't do it. So that's a big mystery.
Yeah.
Maybe for whatever reason, the sun is traveling through kind of an unusual region of ISM with unusual grain properties.
Yeah.
Maybe the abundance constraints are just wrong. So the abundance constraints are sort of hard to figure. We tend to base them on solar abundances.
Mm-hmm.
Solar abundances are hard to measure, as people have done this over the decades. Improving their models, they get really different results from decade to decade with better models of the solar photosphere.
Right.
So maybe there's something wrong there. Maybe the process of star formation just excludes metals somehow. So maybe there's more metals out there in the ISM than there are in stars. So not sure, but obviously something fishy is going on here
Yes.
with these large grains.
Yeah.
We also had some discussion in the conclusions about other types of models. So we were looking here in this paper at the model where the carbonaceous and silicate grain populations are separate. There also are two other really famous models. One where you have the core mantle grains, silicate cores and carbonaceous mantles on top.
Mm.
And then there's the fluffy grain, the composite grain, where you have small dust particles of silicate and graphite, which sort of stick together in a fluffy, maybe almost fractal kind of a morphology. So yeah, we had a brief discussion of that and basically concluded that all those models have their challenges. Our model in particular in this paper, we tried to satisfy the abundance constraints, ended up using a little bit more mass than was really available. And our take on that is that there's basically enough uncertainty that we're not gonna worry about that too much. But obviously it would be great to have a better understanding of what the real abundances are of the elements in dust grains.
Cool. So let me pick up that thread. Um, so that was sort of the state in 2001. Have we made any minor or significant progress since 2001? And if you look into your crystal ball or wave your magic wand, what would you like to see over the next, in the 2020s?
Sure. So there definitely has been some elaboration of dust models. So for example, Bruce and Eigen applied this model to look at other galaxies with Spitzer data, and looks good. There are other models that have been generated that are trying to use more realistic dielectric functions for real materials
Okay.
rather than these constructed dielectric functions like we use. So Ant Jones and his collaborators have a really nice model that does that. But I would say that we still really don't know what dust actually is, honestly. I think it's still a very big question mark. So I've talked so far about two kinds of observations, extinction and emission. But there's a lot of other stuff we could try to bring to bear. There are observations of polarization of starlight. One of the things that is most thrilling to me is X-ray observations. So there's two ways you can use X-ray observations. One, you look at a point source, like an extragalactic X-ray source.
Okay.
Then you get small scattering of X-rays from the dust grains.
Yeah.
And that produces a little halo around the point source. And the structure of that halo is sensitive to the grain properties.
Mm-hmm.
So that's really useful.
Nice.
And then you also have absorption edges. So like if you have any old atom, any element, whether it's in the gas or in a dust grain, basically once the photon energy is high enough to ionize one of the inner shell electrons, then you're going to see a big increase in the opacity, right?
Right.
What's really cool is that if that atom is sitting inside a solid, then you can actually elevate that inner shell electron up into the band structure of the material.
Ooh.
And so you can see structure right there at the absorption edge.
Oh, that's wild.
That could tell you about what material that atom is actually sitting in.
Oh, that's cool.
So yeah, to me, the most exciting prospects for progress in dust modeling are going to be from X-ray astronomy. And so people have used existing X-ray telescopes like Chandra, for example,
Yeah.
to do this. But I'm no expert in this area. My understanding, though, is that to really make progress on this, we're going to need the next generation of X-ray telescopes to do that. So that's where my big hope lies, really, is in that next generation of X-ray telescopes to help pin this down.
So the future is bright going forward. Perhaps using those next-gen X-rays to probe dust properties.
Yeah. I mean, my dream would be to have an interstellar probe, but I don't see that happening in my lifetime.
Dreams are good. Dreams are good. How we get there.
Yeah.
Cool. Joe, I want to thank you so much for your time.
My pleasure.
We are here on a Memorial Day chatting away, so I want to thank you so much for your time. And anyone who is interested in dust grain sizes or has a next generation X-ray mission that would like to probe some dust particles, you can go ahead and get in touch with Joe via email. We won't be putting his email address in the YouTube video or in the description, but those in the game will know how to get him.
Sure. Yeah. Absolutely.
All right. So Joe, thank you so much.
Okay. Thank you, Frank. Take care.
All righty. Bye-bye, everybody.
Bye.